Okay, can you hear me? Yes, it's good. We can start? Okay, great. So, sorry, some technical complications, but we're going to do little less than 1.5 hours, about 80 minutes. I'm going to tell you about this soil data set we are building now. I have some slides. I'm going to introduce things, and then I'm going to do a demo. So I'm going to show you how you can access this data and how to visualize it. And we have a little build up, so people can access that. And we're going to extend this data. We are working on updates, but it is turning to a significant data set. And I'm also giving a next week webinar to GeoLDN, the UNCCD affiliated organization. So they're very interested to use this data as official data set for global land degradation assessment. The data is called OpenLandMap-soildb. It's about mapping soil properties at 30-meter resolution and dynamically, so you can see changes in soil properties. And in a nutshell, this is the app. It's built on top of Google Earth Engine at the moment. And I'm going to give a demo, show you how you can access that and you can see all these things. So I'm quite long in pedometrics and soil property mapping. I did a PhD in 2003 in pedometrics, and I worked then a lot with geostatistics, different kriging techniques, and I was also teaching some geostatistical techniques, and I made my first global SOC map, soil organic carbon. It's not the SOC that you heard there, the socioeconomic data, but it's the soil organic carbon. So I made this one here, and that was in 2009. I wrote this lecture note on how to do basically spatial analysis, spatial modeling, and with different types of environmental data. This book's been still very popular. I always wanted to update it. Now it's 15 years old, and most of code doesn't work anymore. Most of like 90%, I think. And we don't use these geostatistics much anymore, so that's became a bit redundant. But here I started doing just a 10-kilometer resolution, and I was just showing how you can predict this carbon density and using this point data prepared at ISRIC, and at that time was called ISRIC-WISE. And so this was the data, so you can just grab this soil organic carbon data and you can overlay it with different climate variables and terrain variables. And then you fit a regression model, and then I also did that. So that's the regression model. And I also did interpolation of residuals. So here the residuals, so you do interpolation and then you sum up the two, and that's called regression kriging. So that was my first time doing global soil mapping in 2009. So I'm getting slowly old. Then I was in 2010. I joined a Bill Melinda Gates Foundation project to help build the Africa Soil Information Services. So I work about 7 years on that, and I made some soil property maps for Africa. And then in parallel, mainly on my own initiative, I wanted to also do a world, and then I started doing a 1 kilometer, so from 10 kilometer, 1 kilometer, and then I call this data soil grids. I like the name, so it's compact, and so there was a soil grids 1 kilometer first version 2013. And then I made a big update in 2016. It took about 3 years to update, imagine that time. So it was no joke. And then in 2018, we started with OpenLandMap. OpenLandMap is more ambitious. It's general, a lot of land cover, terrain data, climate. So it was actually anything on land. It was not the idea to compete with the OpenStreetMap, but to supplement it with the environmental data. OpenStreetMap is the urban areas, towns, cities, And open land map is soil, terrain, vegetation, climate. So that was the idea, and we saw that there's a bit of gap there. So we said and we are mainly interested in open data. So we started through OpenGeoHub, we started doing open land map. And in 2023, we got a copy of Landsat, and that's where the things really changed, and things started really speeding up. And now we're very excited because now we are actually making a data which is a field scale. So if you go out on the ground and you can really see changes in the predictions we made, you can see that sometimes they match very good with the landscape. So you can recognize soil properties. So this is this new version, the 30 meter, and we made it a few months ago. A few months ago it was released, and there is now also an app. So here's an app, and now runs on the Google Earth engine. And so what you see, we at the moment, we only put few properties. It's not all, we have more data. But the problem is this data, when you do 30 meter, it's a large data, and everything you do with it, takes time. So it's a really big data engineering. The whole world at 30 meter, if you just take the land, I think it's about 300 billion pixels. So you have 300 billion pixels just to represent the land. If you have multiple depths or multiple years, you easily come to trillions of pixels. So it's quite large. And so what I'm looking now here is organic carbon density in milligrams per cubic centimeter or kilograms per cubic meter. It's the same. And we are somewhere here in Perugia. I could go and search it. So here's Perugia. So we are here, and we will now see this soil organic carbon. I can play a bit with the transparency. Let's see. So you see, I can put transparency back, and I can also put a satellite image, so we can maybe do interpretation. So we are here, and I can zoom in a bit further. And so we are somewhere in Perugia. So what you see, soil carbon density looks like the highlands and forest areas, they have a bit higher soil organic carbon. And also we can compare how these things change through time. So I can scroll here and see we have now 4 periods. So we can see 4 periods through time. And I can go somewhere down here. Let me see. I can click on the compare. And now this gives me a comparison. So let's see if I compare the same thing, but these are the most recent predictions, and these are from the beginning. So we can look at whether there's some changes. There seems to be no huge changes in Europe. As you can see, the soil carbon changes relatively slow. So there's no huge changes, but there do seem to be some changes. So I will have to zoom in to see these changes. So you really have to have a good eye to look. Let me see somewhere. I think I see some changes here. So if you look at in the neighborhood of Rome, there seems to be some more urbanization happening. This is urbanization. And that seems to result in a loss in soil organic carbon. So if I zoom a bit more, I can see it. But as you can see, it's a very detailed prediction, 30 meter. I do have to put transparency here. So there will be some places where you have this urbanization, and you see there's a decrease in carbon. The reddish color is the lowest carbon, and the dark green, as you see, it so goes up to 375. Well, there's 37, you have to divide by 10, so it's 37.5 kilogram per cubic meter. That's a relatively high soil organic carbon. The average for the 1.5% of soil, you will have, or 2% of soil carbon, you will have about 12 kilogram per cubic meter. That's kind of the most of the soil in the world, the agricultural soil. They have, let's say, about 2% soil organic carbon in topsoil, and that means it's about 12 kilogram. And I can go also see through deeper soil. Deeper soil suddenly loses a lot of carbon. So as you go deeper, you're almost close to zero. So many agricultural soils, basically, this is zero carbon when you go 60 to 100. But there are some places in the world where you have peatlands and deeper organic soils. And of course, it's a much more interesting, I think, for many people. So now if I zoom out from Italy, if I move to some places where we have, let's say, drastical changes in coverage of tropical forest or peatlands. So these are really some peatlands in Indonesia. And if I zoom into some area, let's take a look here. If I zoom into some area, I can see that there's a, due to urbanization or different reasons, you can see much more drastic changes in soil organic carbon. You see this? So they're really like these areas, because they put plantations and things. So you can see really drastic changes in the soil carbon. If you look, this is 25 years ago and now. Yes, question?
So you have to show trading points. How those trading points relate to what we're seeing on the map?
So yeah, I will explain that. I just jump into this to show you what we're going to do. Screen like I really jump into the point. So this is this data. So that's this workshop's about that. So now we go back to the story, like how was this data made? So I should also say in 2008, people had idea. I think the first person who stood up on a conference and said we should make a soil map of the world. As far as I know, it's a Professor Alex McBratney from University of Sydney. And it was a conference in Brazil. And so he went on the stage and said, let's make because there were a lot of efforts to map regionally soils. But he went on the stage and says, let's make a soil map of the world. And then there was quite some enthusiasm. So they had some meetings in New York, I think, and Columbia University. And then they initiated some initiative to map the world soils. And actually, some mentioned that at that time, there was more budget to map the soils of Mars than to map the soils of Earth. And so that was something, it's too much, so we need to change. And so they started this initiative, and they published the paper in Science, so high profile, Pedro Sanchez and colleagues. And they published a paper, Digital Soil Map of the World, in 2009, I think. 2009, summer 2000, see this paper. And they said we're going to make 100-meter resolution. And it will be, it will match. At that time, there was the SRTMDM. SRTMDM was like a most famous global layer. It was 100-meter resolution, and you could do lots of terrain modeling and things. And then they said, we do it at 100 meter. So we're going to make the world soils at 100 meter. But the discussion was how we're going to do it. So there was no really clear path, I think. They just says, no, we're going to do it. The separate issue is how, right? And then I joined a year after I joined this global soil, they call it Global Soil Map. So I joined it, but I was as a assistant researcher, so I was on a lower level. And then I started thinking practically how this can be done. But anyway, it's very interesting to see 2009, and they thought in few years they will make 100-meter resolution. And actually, only now, from 2 months ago, we have it. So it took how much is that? 15 years. Almost 16, imagine 16 years. So sometimes in science, things go fast. Sometimes we are too optimistic. And funnily enough, what happened is that we jumped over. So that thing, like things went like slow, and then things started speeding up. But we actually jump over the 100 meter. We never went to make 100 meter. We switched to 30 meter. So because the technology changed, and also I was in deeply in the soil mapping. Then I went out a bit, and so then I had to come back. But I started with in 2013. So they wanted 100 meter, and I noticed by 2013 I noticed this 100 meter. I don't know. It seemed already like a big data problem. So I said I want to do a 1 kilometer. And then I did a soil grids 1 kilometer. And Milan here helped develop a front end. At that time, I was focused on data. I just wanted data. And then I asked, they are more like from geoinformatics, they don't do soils or pedometrics, but said, could you help me make some front end? So we made some front end, and we spent about 3-4 years, I think, doing things together and making stuff for mobile phone. And the key was really like, you just like to know what's the soil type. I'm outside. I want to know what's my soil type, what's the soil properties. And then I made in 2006. And then this soil grids, you can see it became really, really popular. It has almost 5,000 citations. Here it says 3,300 and 122,000. It became popular because there was really a gap. Other fields, like vegetation, mapping, biomass, climate, other fields, they had many groups doing stuff. And I think with soils, there was a really gap. And so when I made this, it became like, very easy to find, access, download, and it was split, every property was split. And so it became very popular publication. More citations, yeah. Yeah, so here I see cited by 4,300. So that's the bit of evolution. Became so cited just because of that paper that often happens. I made it to this most cited researcher, Clarivate. I even didn't know that I'm on that list, and somebody told me you're on that list, and then I checked. But just because of this, SoilGrids 250, and it was a lot of work, and I didn't have a dedicated funding, so I improvised, but we managed. Then they made a new version. When I left the group, then they made a new version. They call it SoilGrids 2.0. It had the uncertainty per pixel and things. And now we went and made this in 2000. So 2025, we made the 30 meter. Not all soil properties, but we made it, and there is a publication also. It is still in the review, so it's an open review journal, Earth System Science Data, and now we're making revisions, and so it's still not accepted. But as far as I can see, there's reviews are constructive, and we do want to improve some things, and we want to add more soil data. And this is back in 2016. You see that was the front end that gave make, and it had. I always had this dream that I want something that you can see the predictions. This is soil pH. You see the predictions. You see the training data. And also you see the soil types, and I wanted that you see a photograph of a soil. So when you're outside, then you can look at, okay, how does the soil look like? And you can look at the photograph, and you can do this very quick validation. So that's why we also map the soil types. We also have now soil types in this 30 meter. So that was back, you see that's still my computer, a screenshot of my computer. You can see 2016. I think there's 9th of June 2016. I took this photograph and a screenshot. And then we said we have now 30-meter. It's still not perfect, but it is. I think it's quite. I mean, I have the whole team now, and we switched to space-time machine learning. And the big two things that really change is so one thing is we have this new data, the Landsat derivatives mainly, and terrain variables. So this new data that we didn't have before. And then the second things, we have our own computing infrastructure, and we're running everything in Python now and using a professional library called scikit-map. So that helps us really to bring that to much higher level. And now we can produce global predictions at 30-meter within 2 days. In 2 days, we have the predictions. So as long as we have a point data, and that's still a big trouble, the point data. Well, trouble, let's say it's, they say the modern data scientist job, your 60% is cleaning other people's data. So I think mine is sometimes goes to 80%. So the easiest thing is just to run the machine learning and, fine tune and do the validation and, produce predictions. That becomes the easiest. But this is in a way, the principle of predictive soil mapping is really purely data science. So you prepare the point data, then you do a space-time overlay, and you produce this classification or prediction on a regression matrix. Then you do the hyperparameter tuning, feature selection, and you have the final model, and then you do the predictions. The predictions are 98% of the computing cost, or 99%, because it's really heavy. So that's kind of in a nutshell. And also, I should mention, we started this 30-meter for the world. We didn't say let's just go map the world, but we had a separate project where we did first Europe only. Europe is only like 1/12 of the planet, so it's only like I think 8% or 7% of the planet, and so it was relatively smaller data, and we could do it much faster, and we did more soil properties. We did something like 10, 12 soil properties. So we did this, and then we said, okay, this works. Let's now scale it up to the whole world, and that's how we started doing this global mapping. And we call now this procedure, we call it EO soil mapper, so Earth observation-based soil mapper, because most important data is the Earth observation. So Landsat indices, they're the most important, even though they're combined with terrain variables. But most important is this one in the center. It's the Landsat derivatives. And then we have also this climate data, etc. So that we started first with the Europe, and Europe also made by Gil here. We do it together, but they carry most of the work. And so for Europe, you see we have also, if I look at carbon, so we have it here. And I can also say, bring me now to Perugia. So now we're here. And this one we actually have for every 2 years. So you can scroll and see how much carbon changes. Now it's a bit emphasized, the difference, so it looks like there's a huge difference, but it's not. They're not huge differences, and I can click somewhere, and this will show you that actually there's some changes, but actually they're very small. The carbon changes very gradually, carbon. Only when you have a serious land degradation or some urbanization or deforestation, then you start seeing, these changes. And also what's interesting in the European version, we have trends. So this is 25-year trends. This one is a trend in tillage index. So from Landsat, you can derive a tillage index. And if the tillage index is very high, it means in a year, they probably have a more cropping, And if it's low, for example, if it's close to zero, then it can be permanent vegetation, like a permanent grassland or forest. And then we can analyze this tillage over 25 years. And you put for every pixel, you fit a trend line. And then what you see here, this is just a map of the trends. And if it's a red, it means there's an increase in tillage. And if it's green, the tillage actually decreased. And now I can look at some, I try to find some area. Let me just emphasize this because we don't see it. So I can go, for example, here. Let's take a look. So we see here it's all red and looks to be some field. I'll put this satellite image. So here seems to be something happen. Obviously, this is a new area built up, you see. So they took the vegetation off. But let's say next to it, like here, this plot. Let's take a look at this plot. So now we are really on the farm scale. You can see this 30-meter pixel. You see what it means. And now we're looking at this farm. And so it says here that this tillage, apparently somebody increased the tillage. We can actually now validate it because we integrated the S3 way back. So if I zoom into that area, that's the same farm, you see. Now I can go back to 2014, let's see. And you see they had some other plantation. I'm not sure what they have. I mean, I cannot tell like just looking, but you can see it was covered with a more denser covered. And then we can go 2016. You see now looks like they were doing a wheat or something, I think, right? And then we go to more newer periods, and you can see that there's in the more recent years it's higher chance of bare soil if you compare going back to the 2014. Now I don't see 2014 anymore. I have to zoom out. Let me see. So you can see that there's it was this corner, yeah. So you can see that really changed. They changed it. So and that's why we see that also here on this image. I didn't turn off this one. Sorry. So we can see that on that specific image. So this way now people can and people find it super interesting that they are looking at this like we were here. Yes, this one. So people now they got really interested because they would like to see, and you can see this green and red, they're next to each other. It's very interesting. You can have a neighbors, and one is increasing tillage and the other is decreasing. And this is a European reality. You know, everybody manages land however they think it's the best, and different farmers have different strategy. And this is a new dimension of landscape that it's not visible anywhere. I mean, once we computed this, it became something people can look at. But before that, it was not possible. You cannot see this like 25-year trend. You needed really this data, somebody to process that and to fit these models. Because imagine for each pixel, for Europe, we fit models. I'm talking like millions of models we have to fit, and then we save these parameters of the model. In this case, is the beta coefficient. Like in a linear regression, you have a beta 0 and beta 1. Beta 0 is the threshold, and the beta 1 is the slope. And so we get these different thresholds. And so now we can compare and we can see where's the most red. And we did it for the NDVI. We did this trend for NDVI also. Also very interesting to see where's the long-term trend in NDVI negative, which can be very different from tillage trend. And we also have a bare surface trend for every pixel in the year. Once you have like a 6 to 12 images of soil per year, you can estimate how much is the soil bare. And usually the soil stays bare because people do more plowing or they do more tillage, and then the soil is bare. But some places we have a grassland, it can be whole year, it's covered, so it's never bare. So we are looking now at the NDVI, and I can again zoom in somewhere, it doesn't matter. So here's some area, let's take a look. So here seems to be negative loss of NDVI. We can maybe take a look in 3D. So we're looking at 3D. Sometimes it's interesting to look at the landscape also in 3D to see whether that has to do with some erosion process. I don't see it, but let's take a look now. This is a loss in NDVI. So let's take a look why it happens. So I go to survey back again, zoom in. So there's this area. Okay, so I see also it looks much greener, right? I'm not sure why they had it. It could be that there were grasslands. And look at this, in 2016, they started more intensively doing some crops. And right, you can see it. So if I go 2014 back, you can see often it's switching from grasslands to cropland, increasing tillage results in on a scale of 5 to 10 years, you lose some biomass, you lose NDVI, and so that becomes visible. Now, the second question is, does this have an effect on soil carbon? So I can now say, I want to compare here. So I have this negative NDVI, but I can go and switch to carbon. So I'm looking at carbon density. So we're looking here, this is all red. So let's see if this had any effect on the carbon. So now I'm visualizing carbon, trying to see. Now it's a bit difficult to see. I will have to get like a trend line. So let me turn this off. So let's go for carbon. So if I click on some pixel where it was red, let's take a look. So it doesn't seem to be a much difference in soil carbon. So it kind of went up and down. So in this case, I don't see a distinct difference in there was a little, it started going a bit down, but then it goes up and down. So it's not a distinct. And also when I scroll through time, I don't seem to see the big carbon changes. Even some places look, they have a higher soil carbon in recent years. We can also look at the soil pH. So here's soil pH. Does it have an impact on soil pH? Again, we can scroll a bit. This one there seems to be some difference. Let's see here. Oh, this definitely looks like there is a difference in pH. So the pH looks that it increased from like 7.1. We're looking at the topsoil 7.1. It increased to 7.4. So there seems to be an increase in the soil pH. It gets a bit bluer. It's higher. And you can see it also here. So there seems to be an increase in, so the soil pH becomes a bit more alkaline. We can look at the wide area. We see also distinct trends. So there seems to be some parts that are becoming more alkaline. This is typical that the forests, they have a more acidic soil and agricultural land. As you expose it, the organic matter drops and the also pH then increases.
They have more organic person or this.
Yes, usually high organic carbon is a lower pH. So that's a usual thing. So that was for Europe, and as I said, we said, okay, that works. Now let's scale it up, do the whole world. This is for Europe. We actually produced almost 30 terabyte of data now. And we are going for about 100 terabyte by the end of the year. We're now working on a monthly products of tillage and bare surface and etc. And we're going to integrate way more data for Europe and the Ecodata Cube. And also we have for soil organic carbon, you see it's a kind of 3D plus time. So you have the surface, deeper soil, you can go through different depths, and you have the time. So it's called 3D plus time. And we have the uncertainty also. You can see some places, this uncertainty here is quite wide. It's a wide uncertainty. Here it's a bit more narrow because it's also smaller values. Where we have a higher soil organic carbon, you always have a higher uncertainty. But we also can provide prediction intervals for any prediction we actually provide as maps. So you can, anywhere you click, you can get it. In the meantime, we also produce from Landsat, we produce a bi-monthly GPP, 30 meter. To my knowledge, is the first ever high-resolution GPP. GPP stands for gross primary productivity. It's measured in kilogram per hectare per year. It can be also adjusted to get NPP, which is the net primary productivity. But we started with the GPP. Now we hope to slowly down to NPP. But we have the first 30 meter for every month. Well, now we have a B month. We have six year. So it looks something like this. And so this is gram carbon per square meter per day. And so it looks something like this. And so we produced it from Landsat. Once we process Landsat, we could do GPP. And then we prepared all this data, so terrain variables, Landsat indices, everything for the whole world. And we said, okay, now we overlay soil properties, and then we map the soil types and soil properties globally. And this was the theme. So we had inside OpenGeoHub, mainly Davide, Shumong, and me. We did most of the work with the modeling. I did most of work to prepare the covariates and the point data. And David and Shumong, they were leading fine-tuning, machine learning, and David was leading the prediction process. So that's how we got organized. And so we prepared the data, and we got the help. When you do European, you can do meetings in Europe. It's easy, but when you do global, you need also help on different continents. And we got a lot of help from Travis Naumann. And he was really great because he helped us prepare US data. US data is the biggest soil laboratory data. So he really helped prepare that. And also Jose Safanelli, he's at the Woodward Climate Research. And we worked together for about 3-4 years on the open soil spectral library. And this global prediction is also largely based on that. So because we had all this laboratory data, we were able to combine it. To show you just, so like I said, that the 70% of the work of data modeling is preparation of data. So this is the data, the training data, the point data, and we do it in a quite a reproducible way. So we document all the steps of importing different data sets and binding them and things. And so here we have now at the moment there's about 50 to 55 data sets, maybe 55 data sets. And for each data set, I had to prepare import code. So for each data set, I import it, I check things, I harmonize, I do checks. And so I do that data set by data set. And I'm just doing it. You see, there's a lot of code. This is the shortest code possible, by the way. I cannot make it short. I'm getting good in programming. This is the shortest code. All this stuff I had to do. I had to check things. I had to check distributions, check the values, remove artifacts, remove typos, check, then harmonize, convert to one measurement unit to the other. So this is the shortest code possible. And here you see I made about 2,000 lines of code. So to import this 50 data set, if you scroll through, it's a long document. So it's about, and I do also a lot of visual effects. Everything I import I do visual check. I also plot what's the distribution of points. I do these checks. For example, you take a organic carbon content, and you want to see how the data sets, different data sets, how they stand. And you see that there's some data sets which is from tropical peatlands, and they have all high soil carbon. And then you have some other data set lower. But I need to I do a visual check as an expert. I see whether some data set sticks out. And then I check why is it sticking out. Like, for example, this data set sticks out, this data set sticks out. It's the very high values. But then I say, yeah, this data set is the to be expected. This is Alaska data from some frozen organic soils, I don't know. And so they have a very high soil organic carbon. And then this is tropical peatland data set. So I can do the checks. And this way I check that everything is fine. And then I do also these two-dimensional plots. These are the two-dimensional plots. So I know that sometimes the grouping in data is really hidden. So you see here, there's some grouping. Here, there's some line. You see the red line. So I have to do these visual checks, and then I zoom in back in data, then I change the code and I rerun it, and eventually I do a bind. So this is a bind. This is a very generic function that looks for, so you see it says 50 data sets, and then it binds everything seamlessly into a one final data set, which should be analysis ready. And this final data set, I write it down here, say final analysis of the objects, and then it's just a geopackage or just a table. And then it's really ready to go. And then they do space-time overlay, they do all this modeling, etc. So, question?
Yeah, so on the soil carbon, so the whole lab produced data, right?
Yes.
Certain protocols, and check all the protocols in the different laboratories.
Yes. There's a FAO with the Global Soil Partnership. They had a really nice like a program running for now, it's more than 10 years, I think, where they compare different lab methods, and then they write guidelines how to harmonize data. So I will just take it from, so this is how they recommend globally to harmonize, and harmonization is just functions. So it tells you how you're going to translate something. They estimate the parameters, and we just use them. So we cannot afford ourselves to do this inter-laboratory comparison. And so we use that's what the FAO more like. We look at the literature, and then we use that to translate. As you see, there's also points in Africa. And also I took a data set, which is all the mountains, peaks of the world, I think. So you see there's a data set with all the peaks of the world. It's called ultras. So then you ask me, like, why did you do that? So here the ultra. So you have here it's about how many points? I think it's a few thousand points, which is all the peaks. If you go to Italy, maybe there's like, I don't know, 30, 40 peaks. Right? It's like the highest tops. And somebody maintains these ultras. So what I do, I take this data here, I import it, you see, ultra. I import it, and then I check whether the land cover of this ultra is snow, for example, snow or bare rock. And then I attach to these ultras, I attach zero carbon, because I have to specify what so-called pseudo observations. And I need to do it because nobody in soil science is going to go to Sahara and is going to go top of mountain. People are not crazy. They like, let me go in. But we know as experts that there is actually zero. There's no soil. Many places we know there's a bare rock, there's no soil. Some places you could have a lot of rocks, but there's a little pockets of soil, right? It's possible. But if you look at for example, mountain tops, Himalaya, that there's no soil organic carbon. There's no vegetation, it's also minus, I don't know, 20 or something. right? So we had to insert all these pseudo observations. There are not so many. I mean, it was only like a few thousand, but the machine learning needs to know that. If machine learning doesn't have it, that's a very interesting discussion now, and I can show you that. So we submitted this paper in the Earth System Science Data. So we submitted this paper here. Yes. Where's the paper? This paper. We submitted the Earth System Science Data. Now things started speeding up. There was nobody doing global soil mapping for a couple of. We submitted, and there was almost in the same week another group suddenly in the same journal, they submit a paper also mapping soil carbon. So here, at the same week, imagine, in the same journal. It's incredible, yes. And they did it at 100 meter, and they didn't do dynamic, they do static. So let's say at order of magnitude less complex than what we did. But still, they did it. They made a 100-meter resolution, and they made the predictions. And but they didn't use the pseudo observation. So this is an area in Alps, European Alps, and because we use the pseudo absences, we predict close to zero soil organic carbon density. Yes, but they didn't use the pseudo absences. So some of the models they extrapolate, they go, ooh, with the elevation, as you get higher, soil organic carbon goes higher. And so what happens is they left that model like that, and so the model extrapolates where you don't have any points. It's extrapolation. So they predict very high soil organic carbon. You see, that's their data set. And if you look at the satellite image, the very high resolution image, I mean, you're talking like top of the mountains. There's really bare rocks. There's the colluvium, there's gravel, but there's no soil. I mean, you can see it visually. So the chances that you can have a very high soil organic carbon here, very low, right? And and in our case, you see this is on the left is our prediction, and this is there. So in our prediction, you can see also if I go now to the world soils.
No, that's the same request or the different.
I don't know. I have to check. But yeah, it's there's another group also in the same month also submitted global soil carbon prediction stuff, and I also find out, but it's another journal, and they call me to review that. But it's really now suddenly it's lots of things are happening. But so you see, this is our predictions for the Alps. I need to turn this off. Now we will see also the training points. No, come on. So here's the Alps. And you can see our training points here. So they should pop up. So we have these pseudo points. And you can see on the top of the Alps, we predict close to zero soil organic carbon. And this is these peaks. You see that's the peak. I know this. These red points. So we put this. And you see it's, if you look at on transparency, you can see it's really snow. Think it's the glaciers, right? So we predict zero soil organic carbon, which is, I think, correcting. Do you see this? But in other groups, they don't these pseudo points, and then they will tend to predict very high carbon in these areas. So these are these things with the soil modeling and soil mapping that I've been doing for 25 years, and now I think I'm getting better at it, and I think I understand it. And so that was this thing.
When you find these discrepancies, is there some kind of in situ observations that you can do to validate what prediction is actually?
So we are now, we want to turn this up into something that people can go anywhere in the world and they can see the predictions we have. And they said, no, I have a project. We actually sample here. And that's actually this slide I want to show you. Like somebody does a local project. Says, no, we sample here soil organic carbon. And if they're willing to share it with us, we now have a fully automated system. This EO soil mapper. So it's a really robust machine learning. We have now almost 1 million laboratory samples just for carbon. So imagine 1 million. So when if somebody will share these points with us, we can just add it. And we show this is a real example where we add these points. We add it to the big bulk and we recompute everything. And then we adjust locally. That's the power of machine learning. So locally, we improve the predictions. And you see around it doesn't change too much, but locally, it improves the predictions. And then we can make, with every version, make better and better. So we would like to do every few months, we would like to do an update of all the important variables. And this way we make better and better maps. So the accuracy starts going up and until it stabilizes and just slowly improves. We are now starting with that. And it is happening. People are sending us now points. There's a new point data set from China. There's a new point data set from a group in Latin America. There's a new US data set. So now we already have another 20,000 points. We add them, we recompute, and again, and we just make it. And this type of approach to mapping, it's actually very common in meteorology. It's called reanalysis. Have you heard of reanalysis? So they have it in a couple of projects in ERA 5, which is the climate data, which is reconstruction of the past, 20 years climate. And they do this reanalysis. So as they get more data, they recalibrate the models and repredict everything. And so that's called reanalysis. So it's a gradual improvements. We are now doing that with the soils. So we're really following the paradigm of de facto climate science and the reanalysis, ERA 5 graph, etc. And so we are doing that. But it's a very computational. It's still a relatively high cost. We are now trying to reduce complexity. But the idea is to have within 40, if we get new data, that we update. And then we publish, as soon as it's ready, then we publish a new version. So it becomes like I'm maintaining a software, really, or maintaining a database or some global model. So that's to answer your question. But this group, they published and they have here in the Alps, they have these high values. And also they seem to be, they have some artifacts, I think, from what you see here. How does this look to you? So you have this blocky structure. The soils never have these blocks, soils. These patterns have nothing to do with soils, right? So where this pattern from? No. The blocks here. So these blocks are about 4 by 4 kilometers. I measure them. So they use the climatic data sets together with so they have a multi-resolution data set, but it looks like they didn't downscale the 4 kilometer. They just use it as is. And climate is often important for soil carbon. So it does correlate, but they never downscaled it. So you have these patterns of 4 kilometer, they remained. Because I don't know now whether which variable is it, but more likely it's climate or it's some very coarse land cover, would be also very coarse land cover product. And then also we notice, this is a part in US, we predict much smaller carbon density. They predict a very high carbon density. And it could be that because they didn't have so many bulk density, they think these are really so large areas of peatlands. So something possibly also went. So when we did this global soil mapping, I don't know how much more time I have.
25 minutes.
So, okay. So when we did this global soil mapping, so the paper, I'll open it. So here's the paper. So usually what is very interesting, and so it takes a lot of time to prepare this point data. You have to clean it up. You have these pseudo points, peaks of the world, this thing, that thing. Done like in, I don't know, the preparation like months, and then to get the interesting things is just hours, you know. And then usually what is very interesting is variable importance. So we look at this variable importance. Let me see, where is that plotted? So here's the variable. So that's super interesting because now you see what is really the key to mapping, for example, soil organic carbon density. What is the key? And we notice that the key is NDVI and GPP, this product that we developed independently, has nothing to do with soil mapping, but independently we made it. It came up in top three for soil organic carbon. And it is a very important discovery because now we have a scientific proof. We have a scientific proof that if you degrade productivity of land, you will degrade also soil carbon. We kind of knew it, you know, that it is probably very important, but now we have a scientific evidence based on almost 1 million, you know, different types of samples. The highest quality is about 300,000. And now we have a scientific proof that is really if you want to, basically, if you turn that, thinking other way around, if you want to improve soil carbon, improve soil health, what you should work is increasing the GPP over the scale of a couple of years. So that means, you know, permanent crops, permaculture, sorry, what's the call, perennial crops, then switching to grassland, you know, doing anything that helps increase productivity in the sense of photosynthesis, biomass, etc. So we have it as a scientific proof, and you can see that also in some animations. I think if I have them, well, I can just show you that I think it's here on the, so you can see it here. This is an area in Brazil where you have in Amazon. And you can see this carbon slowly being depleted, and it's related mainly with deforestation and urbanization. So you can see that. So somebody says, okay, we want to increase soil organic carbon. Now we say globally, if you want to do something, focus on the GPP, focus on land conservation, and this is the way you can long-term increase soil organic carbon. So we have it as a scientific proof. So that was, and it's also visible if you go, let me go in the app. So what I'm going to do now, I'm going to go to Brazil. So let's take a look at here. So as you can see, this some states in Brazil now there's a lot of conversion of land. You know, if you look at the many areas in Brazil, well, I can open the OpenLandMap for that. Let me see. So you see, if I look at some parts of Brazil, I can scroll through time, and you can see this used to be a lot of forest, and then it's been converted See? This is from 1985 land cover. It's 30 meter actually. You can see very high resolution. You can see how landscapes are being transformed. So you see here. So there's these areas where there's a lot of conversion of tropical areas. And now we can maybe look at that, scroll through time. So scroll a bit through time. This one is a bit slower because it's running on Google Earth Engine, but let me see if I can find some area. So there must be some areas where, because of conversion, I think I have to zoom in, otherwise it's too slow. So let's take a look at here somewhere. But it is a bit more difficult, I have to say, for carbon, because lots of places carbon is actually small values. And to notice where the changes are, maybe I can click somewhere. Let me see if I try this one. Try this one. So now I just click on some location. Okay, so here. So look at this now. This is an example. So this was a forest patch. It was a forest patch, and it was converted from forest to some pasture or some cropland, and you can see the organic carbon dropped. So they lost about 40% of soil organic carbon over the 25 years. So we can really see it now here, and you see if I go back in time, you see it's not reddish. And then in this year here, when I go to this period, see it becomes reddish. So most likely they lost the carbon here, and it is most likely because of the deforestation and the conversion of land. And you can also almost see it on the satellite image, right? You can see it. There's probably also maybe some erosion happening because of that. But this way you can see what is this effect of this land use on the carbon. And we can you have this little tool everywhere you click, you will see how much carbon you lost approximately, and you can see, for example, here there's no loss of carbon, but here there seems to be a loss in carbon. Okay. So now this app, we just have to keep on improving. As I said, now it's in Google Earth Engine. I don't know, we will also integrate it in OpenLandMap, the main website. Need help from GitHub here to do that, and then it will be all much easier to use. This data is also available if you go to the landing page. This data is available. You can also just load it in a QGIS. So that's also possible. Let me see, I have to find. So here's, for example, the year. Yes, this is the year 2000 to 2005. I just take this and I put it into QGIS. I can just add it as a HTTP file. One more time. Copy. No, this one doesn't work. I don't know if they maybe changed the version of the file. This one is working. So here I have it in a QGIS, so it's a whole world. And I can also zoom in somewhere. And I can also export this data, but now I have to set up a kind of legend and things because it doesn't come automatically. So I'll just put something simple, some, I don't know, yellow, like this. And maybe decrease this a bit to 40. So now I have this whole carbon data also in QGIS, and I can also do modeling. I can put also satellite image in the back. Let's put a satellite image. So here's a satellite image and also play with transparency, right? So if you say I don't this doesn't work for me, this like it doesn't work for me to transparency. Yeah.
Let's move down the satellite program.
That's okay, but if you don't want the transparency, you can turn it on and off. But you can see now there is this carbon in the predictions. We can see this area where there seems to be some deforestation again. And so it is visible that we are probably losing here carbon. Okay, so it's also possible to load it into QGIS and do local analysis, even though it's a huge image. This one image is about 140 gigabyte, right? But you can just drag and drop in QGIS, and because it's all cogs, and you can do seamless overlay, you can put polygons and things. And I did it actually on Tuesday. I gave a little demo. So I was showing them. They gave me an actual farm. And so they wanted to know, okay, this is my farm. What can you tell us, like how much the soil pH changed? And then I was just, I can just overlay this pH. And again, I can play with the transparency. So here's the transparency. So I can overlay and I can show them how much is a 30 by 30 meter pixel, etc. So you can also seamlessly integrate all this data into QGIS. There is also for those of people that would like to speed up a bit and also know how to code, we have also this tutorial. This is in Python. And this one has basically everything. So you can overlay points. You specify some points. So this is 2 points. And then you can query all this soil carbon. And you can produce distribution with the uncertainty. This is for Kalimantan in peatland, and this is somewhere in Tibetan Plateau, much smaller carbon. And you can also do these plots through time with the uncertainty, and also plots through depth. So this tutorial explains all these things, how you can do it. And I can show you also, I can do it also in R. So I will just specify the location of the file. So here's the location of the file, right? This is a soil organic carbon for 2005 to 2000 soil organic carbon data. And it's for, so I just have to, I specify that as a remote file. They just specified as a remote file. And then you see I can put like a pointer to that file. So I didn't load it. I didn't download it. I mean, it's 130 gigabytes. It would have taken one afternoon on this Wi-Fi to download it. So I don't download it, but it recognizes a spatial raster because it does a HTTP query to that file and then just get back the meta tag. So no values, just a meta tag. It says, oh yeah, I'm a geospatial file. And I see the dimensions. The file size is 500,000 by 1.4 million pixels. This is the globe at 30 meter, 500,000 by 1.4 million. So it's a huge, huge image, okay? And I specify it, and then I can specify some point. This is the point in China. And then I do an overlay. And this overlay returns me the value of the soil carbon at that location. So without downloading the data. So it works almost like API. This is how you work with the cogs. And this way you can also do a lot of modeling analysis and get it for some farms or polygons, as long as you don't have a huge polygons like whole of Europe or whole of Spain. You can also fetch all this data, and you can make little application solutions that are built on top of this cloud optimized data. And now as we improve this data, it's going to be denser and denser. There will be more and more data. We have soil types, we have a pH, we have texture, soil texture fractions, sand, silt, clay. And so there will be more and more data, and it's going to become richer and richer.
And that's this.
Yes?
Do you also have chemical data like calcium, magnesium, sodium?
Yes, it's possible. We did it for Europe. We have more properties. So it's possible to do what's called nutrients, soil nutrients, and also the soil micronutrients, so anything I think which is below, I don't know, 150 ppms, it's like micronutrient. So it's also possible. We could also map it.
For me, it depends. Because I do this chemical analysis for you the other, and just to have two, and it doesn't, the more the merrier, right? But if I just have like one or two elements that I can already check through this kind of interface would be perfect.
Yes, I did map it for Africa, and this portal also with Milan and Gilab. It's called ISDA Soil. We mapped nutrients and micronutrients for Africa. So you see here. And here you can see really also, like what you said, chemicals, I don't know, magnesium, right? So this is the magnesium concentration, calcium, iron, zinc, So this thing we also mapped. And we have also chemical soil properties, even this cation exchange capacity and things. So we did at 30 meter, but now it will be nice to make that at globally. Now, okay, I cannot promise you too much, it's not going to be this year, but I think next year, as soon as this takes off a bit, we do also would like to get somebody to help us with this, and I'm talking philanthropy mainly because we make it as open data. So it will be nice to get some philanthropy to support it, so we just maintain it really and we make it better and better. Or we get some project, so that's a bit. I noticed now the many projects like European funding is just to make European data usually, and there's really not a lot of funding. I will still say we are in this world where there's way more money. We're talking billions of euros, dollars, to have a mission on Mars and to map the source of Mars. Then to say, it will be very useful to know about soil health, soil nutrients, where are the gaps. And there are many, when we, well, there's so many surprising patterns because you don't see this, soils you don't see on satellite images. So you really, you need to have a lot of samples and you need to build models and then you have to predict. And so absolutely would like to do it. We have a capacity, but this year for sure we're not doing soil micronutrients or something. It's just too much. We will probably do the Africa one more time. We're just waiting for new point data. There's a new data set that produce new point data, but we don't have access. So again, it's the point data. But we would like to map nutrients and micronutrients and chemical soil properties. First for Africa, and then probably global. And then global, we would like to do a space-time so you can see changes. It might turn out to be some scary things, we're losing maybe some phosphorus somewhere, I don't know, but I don't know. I'm not to solve politics, I try to stay out of. I just want the best possible data for openly for everyone. So what does it going to say? I don't know. Whether it's depressive news or we do see for this thing I showed you this is the like a real there's a deforestation. We see it leads to the degradation, but maybe some places where they do irrigation systems. I mean, for example, here in the delta of Nile, we do predict that its soil carbon is higher. So for sure, it's higher than if they didn't do irrigation, and maybe many places there's an increase in soil carbon. So there's also what we call champions of the land. The soil carbon is like it's an asset, right? And I asked Ishani, my partner and wife, and so she's a hardcore soil scientist and agricultural expert. So I asked her, is there any negative side effect of soil carbon? Is there any negative? And I asked also Pete Smith, Professor Pete Smith, and this specific question says, yeah, there can be, for example, if you add manure, which is, let's say, has some pollutants or something, and if you add it in the soil, you increase the soil carbon, but you add this some pollution, or you add too much nitrogen, and then nitrogen leaches and goes in the groundwater. So there are some negative side effects. But let's say these are few extreme cases. In general, 90% cases, soil carbon is like in general, it's like being more fit. It's like anybody being more fit. So it's the fitness of the planet, really. And we really all have to work and not to increase soil carbon like small areas, not like 1%. Like we need to work on increasing soil carbon on massive scale, right? Because soil carbon means the soil also has a higher soil water holding capacity. It has a higher biodiversity. It's less prone to degradation, erosion, etc. It causes higher productivity. It has this cycle of increasing productivity. So soil organic carbon, we have to really increase it all around the planet. And we could increase it at least 30, 40%, because that's how much we lost due to all the industrialization and all this thing we did with the landscapes, removing forests and stuff. We remove about half of the original forest, right? You know that. Soon we will have more than 80% of tropical forest removed, So just returning that productivity and returning soil carbon, it's an interest of the whole planet, of the human species, That's kind of fundamental. It's a fundamental thing that there shouldn't be any discussion. I mean, we should have a taxation system that value that, and that whoever makes, you want to invest in soil carbon? I know, but we should have a whole taxation system that any areas, any regions, NUTS 3, whatever, that show that we increase soil carbon in 10 years, like 10% or something, that they should have benefits, because it's a fundamental thing. It's a no discussion. I mean, exactly. It's like a freedom of speech or democracy. That's to landscape its soil carbon. And that's why it's very important to monitor it, right? It's very important to get it, to understand how much carbon we lost, That's why we did these dynamic maps. And biggest places where we lost soil carbon also, it's very important to see that it's kind of, it has a very skewed distribution, right? If you go to some areas, I don't know, in north of Russia and Canada, you have these peatlands. So there's a northern hemisphere peatlands, right? And you have these huge concentrations. I think almost half of the soil carbon we estimated in the world is in Canada, Russia, and then also a lot of pockets in tropical peatlands. So if you go also to Brazil, you have these peatland areas like here, and also there's a lot of pockets of carbon there. So if you lose the wetlands and peatlands, mangroves, you can lose a lot of soil carbon in the total sum, not huge areas, but in a total sum, use lots of carbon. And then also any degradation of land, lots of GPP, we have a scientific proofs that leads to loss of soil organic carbon. So that's what we try to produce with this open land map to get that sorted. So, yes,
According to the modeling books of organic carbon. So the most important predictor is soil depth.
this is purely because the carbon drops very exponentially with the depth because of that. But beyond that, it's NDVI and GPP, and then it's rainfall. The Chelsea Bio 5 is the annual rainfall, I think. So that's on the top.
This soil depth, it is not depth of bedrock, it's
Just the depth at which you take samples. So and you can see that if I look through the if I open here different depths, right? You can see how the carbon disappears very abruptly. So it's a really exponential fall. They follow what is called a log-log function. Just a second. But this is the log, I think, bulk density, but I had it somewhere. You can see that it's very systematic. Maybe here somewhere I have it. Yeah, the depth of the soil and soil organic carbon, and both are plotted on log. And you see it's a linear. It's a linear on a log-log plot, right? You can see how it goes. But somewhere it's a bit more complicated. Like here, there was some, some cluster which sticks out a bit. But in general, it's a log-log linear relationship. There is also other products. We make some soil products, but our colleagues at the German Space Agency, they also made this. It's also fantastic. They at the moment they have it only for Europe, but also they actually the first time ever they mapped the color of the soil. So this is for the whole continent, which is amazing. This is from Sentinel-2. So they take 3 years of images and they look for pixels when the soil land has almost no vegetation, so it's like a bare soil, and you don't have it so often. So that's why they need 3 or 4 years. And then if they have once in 4 years, you have a soil is bare, they can see the color of the soil. And so this is the soil image of the planet. Well, starting from Europe. It's also funny the effect of GDAL. If you look, if you zoom out, then you think, oh wow, they have they stripped all the vegetation. But when you zoom in, actually you can see that actually there's huge gaps. And because the forest all around. But because of this GDAL resampling, it ignores the missing, so it kind of fills it in. So on the end, you have something like this. And you can see these Ukraine soils are darkest, that's known also, and the forest soils in Scandinavia, they have a more organic carbon. So
it ignores the green at the higher scale.
the gaps, yeah.
Then okay.
It fills it in, So you can see it as I zoom in, You notice actually it's way less pixels. It's only about 1/3 of pixels. In a 5-year period, you will have no cover, right? And then you can get this. There's another ways to maybe remove so it's called a spectral unmixing. There's another way to do it. I don't use that, but you cannot do magic, right? If you have a whole year forest, if it's, for example, boreal forest, the needles a whole year on, and if it's let's say very dense, you cannot see the picture of the soil. I mean, it's not possible. So this you have to look.
How do they account for rainfall? I mean, rain changes the color. But I have sand ground, which is usually gray if it's dry, but black if it's wet. So
no, this thing. I mean, you can do multiple years, and then let's say 1 year it will be maybe dry, wet, and then kind of you cancel that noise. So this is called interannual variability. This thing with the dry, wet. Interannual variability is a big problem for predictive soil mapping, and I'm aware of it. I suffer with it for like years because I had some models, and then I was like saying, oh, those predictions go up and down. What's happening? They went up and down because interannual variability. So that's why we do block predictions, we predict in blocks. And so these blocks, they look like this. So when you predict, you smooth out. So here the blocks. So we take one pixel that you see prediction actually has 4 points. And so we remove interannual variability, and we also average to have 0 to 30 centimeters, 0 to 20, right? So we do this kind of blocks. And that's also important. We are still, we run, So yeah, thank you for listening. Thanks for the questions. So this was a bit of personal story, and it is not this front end. I mean, you see, I'm trying to reach something, but it is a bit slow. You have to be a bit patient, but the data is there, and we can just make a better and better system. So from this point on, I mean, it will just get better and better, more data, better accuracy, easier to use. So slowly it will come better and better. It's just basically it's just the beginning. That's what I say. After 20 years of testing, now I can start doing the real stuff. Yes. Yeah, that's how it goes.